Hey there, everybody. We have made it to our final week of new material. How are you feeling? Hopefully excited about finishing up this year. I know it's been a very strange year, and summer is right around the corner, and then we'll have a fresh start next year. So I hope you guys are in for a good week this week of chemistry, and then we'll wrap it up. So we are going to talk about enthalpy and thermochemical equations today, both of which are fairly new terms for you. So let's just go ahead and dive in. By the way, art of the day is the Berlin Wall. The Berlin Wall, as you can see, had a lot of graffiti on it. It was an amazing, repressive wall built in Berlin that separated the city, and it was very joyous when it came down. And I thought, it's pretty good art of the day. I don't really know how it relates to enthalpy or thermochemical equations, but I like the celebration of tearing down barriers. So here we go. We've talked about this already, the direction of heat and processes. And any time that a reaction or a process produces heat, we call that an exothermic reaction or an exothermic process. Exo meaning to leave, thermic meaning heat, so heat's leaving, and these processes always feel warm as the heat leaves the process. If energy is going into the system, then we call that an endothermic process or reaction. Endo meaning going into, and thermal still meaning heat, so heat going into the system. So these are two directions we've talked about before. You should feel pretty comfortable with these terms at this point. A new term that we're going to be talking about today, though, is enthalpy. And enthalpy is very much related to heat changes, but under kind of special conditions. Enthalpy is the heat content of a system at constant pressure. If the pressure stays constant, then it's the heat content that the system contains at a moment. If the pressure changes, then the enthalpy changes also due to that pressure change. But we are not going to talk about that. So for our purposes, enthalpy, which is given the symbol capital H, means heat. And most of the time, we talk about heat changes. And so we're going to talk about delta H, meaning change in enthalpy. How much heat does a system have initially versus how much heat does it have after the process? And the reason we talk about changes in enthalpy is it's really hard to measure enthalpy at a moment. But measuring changes in enthalpy is actually pretty easy because we can measure the heat that comes off of a reaction by temperature change, or we can measure the heat going into a reaction by that temperature change. So for our purposes, Q system, the heat of a system, is equal to the change in enthalpy, delta H. I don't know why enthalpy is called H. I should look that up so that I can tell you. But it's nice that it's H because H and heat go together. So Q system is equal to delta H, change in enthalpy. Delta H is negative for exothermic processes and positive for endothermic processes. And this matches the sign conventions that we talked about last week. Anytime heat leaves a system, it's negative. Anytime heat goes into a system, it's positive. So for chemical reactions, we put a little subscript. If you look at this, you'll notice that we have a little subscript here, Rxn. Delta H with the subscript Rxn means the enthalpy of a reaction. And we're specifically going to be talking about reactions today, enthalpies of reactions, not physical processes like melting or boiling or anything like that. So this is energy that's either absorbed by a chemical reaction or released by a chemical reaction as the reaction takes place. So one way that we can represent the energy being lost or gained by a reaction is by what's called an energy potential diagram. And we're going to look at two different energy potential diagrams, one for endothermic and one for exothermic reactions. So here's our first one, exothermic. If you'll notice, we have potential energy on the x-axis and we have the reaction pathway, which just means the reaction as it takes place. So the reactants have a high amount of energy stored in their bonds. When those bonds are broken, it takes energy to do that. So we have to put energy in to break the bonds of the reactants. Once we break the bonds of the reactants, then the reactants are capable of rearranging the atoms and forming the products. And as the products form, the energy decreases, and we end up with low energy products. So we have high energy reactants, low energy products. The energy it takes to break the reactants apart so that they can react is called the activation energy. The activation energy. And you can see that right here, and that's a term that you do need to know. It's abbreviated E with the subscript A, and notice that it's kind of like this hump in this diagram. It's the amount of energy that's just needed to get the reaction to go. Once we get the reactants broken apart, they create what are called an activated complex. And these are just the atoms and ions that have broken apart and are now ready to form new products. Then the energy goes down from the activated complex down to the products. And if you'll notice, the energy from the reactants to the products, this line that we have right here, is the energy that's released in the reaction. In other words, it's the energy that reactants had initially and the energy the products had at the end of the reaction, the energy that was released to get from the reactants to the products. And that's the enthalpy of reaction, delta H. And again, sometimes you'll see it as delta HRXN, meaning the enthalpy of reaction. So that is our energy loss in this particular reaction. Notice the energy is in kilojoules for this particular product. A lot of times you'll see numbers on this scale so that you can actually calculate the enthalpy that was lost. For instance, if this was 40 kilojoules up here and this was 20 kilojoules down here, how much energy was lost? Well, it went down. And so if you subtract delta H equals H final minus H initial, because remember, delta always means final minus initial. So 20 kilojoules minus 40 kilojoules gives us negative 20 kilojoules. So we lost 20 kilojoules. And notice we got a negative because it lost the energy. So this is an energy diagram for an exothermic reaction. The reactants have higher energy and the products have lower energy. For an endothermic reaction, the opposite is true. The reactants have low energy, the products have high energy. So the reactants gain a whole lot of energy in order for them to break apart and make an activated complex. And then when the new bonds are formed, the products end up with higher energy than the reactants had. And so endothermic reactions are not all that favorable because look how much energy you have to put in and you get very little energy out. These are typically not favorable reactions. So notice that from the reactants to the products, the energy is going upwards. And again, if we looked at this, if I drew a little dotted line here, if we had units on here, if this was 40 kilojoules, 40 kilojoules, and this was 20 kilojoules, if we did our math here, delta H, the change in enthalpy, is equal to the final energy, so 40 kilojoules, final enthalpy, minus the initial enthalpy, 20 kilojoules, and that gives us a positive 20 kilojoules. So the energy went up, it gained energy, it gained 20 kilojoules. Notice we got a positive here. Notice the arrow is going upward just to show that our enthalpy increased here. Notice the activation energy is very massive. The activation energy is from the reactants all the way up to the top of the hump there. The activation energy is kind of a barrier to whether a reaction will occur or not. In order for you to get a fire started, you've got to add a match, you've got to get it caught on fire, you got to add energy to get it going. Once it gets going, it releases energy, but you have to add some energy initially to get over that hump to activate the reaction itself. So this is an endothermic reaction energy diagram. So just an important note, anytime that bonds are formed, so if we form bonds, anytime bonds are formed, energy is released. So forming bonds releases energy all the time. Anytime that bonds are broken, energy is absorbed. So it takes energy to break bonds, and you release energy when you form bonds. The balance between these two determines whether you have an endothermic or exothermic reaction. If it takes more energy to break the bonds of the reactants than is released when the products are formed, you have an endothermic reaction. If you have more energy released when the products are formed than absorbed by breaking the reactants bonds, then you have an exothermic reaction. So the balance between these two determines whether a reaction is endothermic or exothermic. So really important, this one. Energy is always released when a bond is formed. Energy is always absorbed when a bond is broken. So thermochemical equations. How can we represent this energy in the equation of a chemical reaction? Well, a chemical equation that includes the energy change is called a thermochemical equation, not just a chemical equation. And we have two ways that we can write a thermochemical equation. One way that we can write it is we put the energy right into the equation. In other words, how much energy was released or how much energy was absorbed, we actually put the number into the equation as a reactant or a product. If it's a reactant, then that means it's an endothermic reaction. Energy had to go in as a reactant to make the reaction occur. If we write it as a product, that means it's an exothermic reaction. The energy was released as a product, and so it would be exothermic. The second way we can write it is by writing the regular chemical equation, and then off to the side, we literally write delta H equals, and we say how much energy was either absorbed or released. If we write it in style 2, we have to use positives and negatives. Positive meaning energy was absorbed, negative meaning energy was released. So we're going to look at a couple of examples of this. So let's look at this. Let's look at an exothermic reaction. So if we burn propane, C3H8, would the energy be a reactant or product? So I want you to think about it. If you burn a hydrocarbon, if you burn propane, butane, octane, any fuel, are those endothermic or exothermic reactions? Well, of course, they're exothermic. So do you think that the heat would be a reactant or would be a product if it is produced in the reaction? Well, hopefully you heard me say produced, so we'd write it as a product. So first we'd write the balanced equation. So you can see the balanced equation here. And then we would put the actual amount of energy. We'd have to look it up or we'd have to calculate it. We'd have to do something, but we'd have to have more information. You can't just make the number up. To write this as a thermochemical equation, we actually put the energy right over on the product side. So when you look up how much energy is produced by burning 1 mole of propane, it's 2,200 kilojoules. So burning 1 mole of propane will produce 2,200 kilojoules of energy. So we write it as a product over here because it's exothermic. Notice I don't put a negative on it because writing into the products makes me know that it's produced, it's released in the reaction. So this is the first way that you can write a thermochemical equation. The second way is to write the chemical equation just like normal, and then off to the side write delta H equals, and then we have to write the energy next to that. So again, we have to use a positive or negative to tell whether the energy was released or absorbed. So in this reaction, was it released or absorbed? Hopefully you said released, and released means negative. So we would write the negative amount of energy that was released in this reaction, negative 2,200 kilojoules. Okay, so that is the second way of writing chemical reactions. What about endothermic reactions? Well, let's think about baking soda. When you heat up baking soda, it produces carbon dioxide. That's why we use it in baking, is because it decomposes, produces carbon dioxide, and that helps things rise. So would the energy be a reactant or a product if energy decomposes the baking soda? It would be a reactant because it goes into the reaction in order to decompose the reactant. So in this reaction, we would put the energy on the reactant side of the reaction. So you'll notice 129 kilojoules. Again, we don't worry about positive and negatives here. We just add it as a reactant, and that makes me know that it was taken into the reaction to make the products happen. So it's endothermic. So here is our thermochemical equation in the first style. The second style writes the same chemical equation, but now we write delta H equals, and we have to say how much energy was either absorbed or released. So in this reaction, we see that 129 kilojoules was absorbed. So is that positive or negative? Well, if it was absorbed, that means it was positive. So we write positive 129 kilojoules off to the side here. So again, really important. In style 1, no positives and negatives. You just write it on the reactant side or the product side. In style 2, oh, wow, I actually have a mistake here. That should not be there. That was from style 1. In the style 2, you just write it off to the side, and you do have to make sure you put positive or negative in that reaction. Sorry about that mistake. Okay, so what must be specified in these thermochemical equations? Well, you have to include the physical state of each substance, because if something's a solid versus something's a gas, it's going to take a different amount of energy for it to react. The enthalpy for the reaction is the enthalpy as it's written. So for this reaction, the decomposition of sodium bicarbonate, baking soda, it's exactly as this is written. So 2 moles of NaHCO3 solid decomposing takes this much energy. If it was only 1 mole of this, if we basically cut everything in half here, then it would be half that energy. So the energy is always specific for how the reaction is written, exactly as is. Okay, so enthalpy calculations. We can actually use these thermochemical equations to not just do mole-to-mole ratios of how much reactant and how much product can be produced, like we do in stoichiometry. We also can use these thermochemical equations to figure out how much energy is released in a specific chemical reaction. We can use the delta H values to calculate the energy released or the energy absorbed for a specific amount of reactant or product. So the ratios in the balanced chemical equation and the enthalpy change can be used in the stoichiometry problem. So let's do a couple of problems with this. Here's our propane example from earlier. This is the balanced equation, thermochemical equation for the burning of propane. And our question is, if 2 moles of propane are completely burned, how much energy is given off? So if you'll notice, you could probably do this one in your head, but we're going to use dimensional analysis to solve this problem. But 1 mole of propane will produce 2,200 kilojoules of energy. So how much would 2 moles produce? Hopefully you said twice as much energy, 4,400 kilojoules, and that is correct. But let's see how we would set it up with dimensional analysis. So we have 2 moles of propane, and from the balanced chemical equation, 1 mole of propane will produce 2,200 kilojoules of energy. Notice our moles of propane cancel, and 2 times 2,200 is 4,400 kilojoules. So our balanced thermochemical equation not only gives us coefficients for all the substances, and we can just do stoichiometry like you've always done, but it also gives us the energy, which we can use like all stoichiometry ratios. Okay, let's look at another example. So here's a propane reaction again. We're going to do the same reaction, but this time 1.75 moles of carbon dioxide are produced. How much energy is given off? So this one's not quite as easy because the numbers aren't nice and simple. So we need to look at this and see how we're going to solve it. We're starting with moles of carbon dioxide. Here's carbon dioxide. And we're trying to figure out how much energy is produced in this reaction. So we're going to start with the amount that we're given. 1.75 moles of carbon dioxide. And then from the balanced equation, 3 moles of carbon dioxide are produced when 2,200 kilojoules of energy are produced. So that's our ratio. 3 moles of carbon dioxide and 2,200 kilojoules of energy. So moles of carbon dioxide cancel. We're left with kilojoules. And now we can multiply across the top, divide by the bottom. And when you do that, you will get 1,300 kilojoules of energy released. All right, let's try another one. Again, let's look at propane again, just because we have it. How many moles of C3H8 must be burned to produce 10,500 kilojoules of energy? Now, this is a really practical problem. A lot of times we burn fuel in order to do things for us. And in this particular problem, we need 10,500 kilojoules of energy to do whatever it is that this process is being used for. So how much propane should I expect to burn in order to do that? So we're going to start with what's given, 10,500 kilojoules of energy. According to the balanced chemical equation, 2,200 kilojoules comes from 1 mole of C3H8. So 2,200 kilojoules of energy from 1 mole of C3H8. Now another step I could have asked is how many grams of C3H8 need to react. So we could do another step and convert moles to grams, which I know you're capable of doing. But this problem is just asking for moles, so we'll stop right there. So we're going to multiply everything in the numerator, divide by everything in the denominator, and when you do that, you end up with 4.78 moles of butane. So in this particular problem, if you have a specific amount of energy that you need in order to accomplish some task, then we know how much reactant I need to purchase in order to accomplish that task. course, that's assuming that no heat is wasted to the environment, which of course we know heat is often wasted. So this is ideal conditions. Okay, let's do one last problem. Here's our grams. I told you grams could be produced. So how many grams of propane must be burned to produce 15,250 kilojoules of energy? So again, we start with what we're given, 15,250 kilojoules. 2,200 kilojoules is 1 mole of propane. And 1 mole of propane, C3H8, each carbon is 12, so that's 36. Each hydrogen is 1, so that's 8. 36 plus 8 is 44. So 44 grams of C3H8. Now notice I did round those to whole numbers. If you get decimals, you'll get a slightly different answer, and I think my answer will include the decimals, so I apologize for rounding there, but multiply everything in the numerator, divide by everything in the denominator, and before we do that, kilojoules cancel, moles cancel, and we're left with grams. And when you do that, you should get 310 grams of propane. So that is the end of this lesson. If you have any questions, of course, please contact me. I'll be happy to help you out with any problems that you have. Best of luck with today's lesson. And remember, this is our last week. Hang in there. You're going to make it. Bye, guys.